What is the underlying assumption here? The underlying assumption is that there is no alien intervention here. There is nobody applying external torque. Hi everyone, my name is Adindapal Singh and welcome to ATP STEM. In today's video, we are going to do one short revision of topic rotation for your school examinations. It's November, many of you are going through your school exams right now, so you don't need so much of detail which is required for JEE Main, NEET or Advanced. For that, we will be posting a separate video. And in this video, I will put up all the chapters, basically all the subtopics that I'm going to do, which you will find in YouTube chapters. I will also be linking up this entire PDF for you to download, review and do a quick revision before the examination. Okay, so let's start. But before we begin, I'm going to do a quick review of circular motion variables, which are a precursor to topic rotation. Let's do this. If an object moves from point A to point B on a circle of radius r, it covers distance L. This distance L is the length of arc. Okay, this length of arc is related to angle theta and r by this formula. L is equal to r theta. This is your length of arc formula. If we divide both sides by t, then what do we get? We will get L by t, which is the speed, and theta by t, which is angular speed. I'll be elaborating more on this shortly. This is just a basic relation here. So v equals r omega. Linear speed of the object, how the object is moving forward along a circular path, is related to its angular speed, angle covered per unit time. If we find out delta v by delta t, then on the other side it will become delta omega by delta t. So what is delta v by delta t? Rate of change of speed. Rate of change of speed is tangential acceleration. It is not centripetal acceleration, it's only tangential. And delta omega by delta t is called angular acceleration. Rate of change of angular speed. What do these things mean? So when we say that omega is rate of change of angle, so omega pi by 3 radians per second means object moves through 60-degree angle in 1 second. Pi by 3 radian is 1 second. If you are not familiar or sure about conversion between radian to degree, let's look at that as well, because some of you might not have taken mathematics in school, but you are doing a physics course. So pi radian is 180 degrees, so pi by 6 is 30, pi by 4 is 45, pi by 3 is 60, pi by 2 is 90. These are your standard angles, right? And these are their conversions in radians. So here omega equals pi by 3 radians per second means object moves through 60 degree in 1 second. Alpha, rate of change of angular speed. When we say alpha is 2 radians per second square, what does it mean? So it means, let's say at t equal to 0, there was an object with an angular speed of 4. So after 1 second, because there is alpha of 2, because there is a change of 2, new omega will be 6. 4 to 6, there is a change of 2. Similarly, in another 1 second, this will become 6 to 8. You can keep going. At t equal to 3, it's going to be 10 and so on. So alpha equals 2 means omega keeps changing by 2 in every 1 second. Okay. Equations of rotation. Just like you have equations of linear motion, v is equal to u plus at, there is omega final, which is omega initial plus alpha t, s equal to ut plus half at square becomes angular displacement equals omega initial t plus half alpha t square, v square equals u square plus 2as becomes omega final square equals omega initial square plus 2 alpha delta theta. Now here, let's say that there is this question, a disk of mass 2 kg, radius 2 meter is rotated from rest to acquire a speed of 20 radians per second in 5 seconds. Find angular acceleration and angle rotated. So in this case, what have they given? They have given mass. Mass is of no use in this question. Okay, what else have they given? Radius is 2 meters. Okay, fine. That is also of no use because we are only dealing with angular variables. If at any point they ask us to convert this into linear variable, then we might use radius. Not as of now. So here from rest means omega initial is 0 and then omega final is 20 Time taken is 5 seconds and we have to find angular acceleration. Which equation shall we use? We should use the first one or just the definition of alpha. What is definition of alpha? Rate of change of omega. Change in omega over time taken. Omega is changing from 0 to 20 in 5 seconds. So rate will be 4. That's it. So omega final minus omega initial by t is going to give you 4 radians per second. How do we find angle rotated? For that we can use second equation, which is omega initial time half alpha t square, 0 plus half 4, 5 square. This will give you 50 radians. Okay. This was the precursor from circular motion which was required to start rotation. Now let us start with actual concepts of rotation. When it comes to rotation, imagine that you have this block of mass m. If mass m is constrained to rotate about that axis, mass m cannot come closer to the axis, it cannot go away from the axis. If we apply a force to make it go this way, then this force will create an acceleration in this body. This acceleration will be given by Newton's second law, F equal to ma. But this is not the right type of variable to deal in rotation. So while considering circular motion or rotation, we should always try to use angular variables: angular displacement, angular speed, and angular acceleration. So how do we convert this into angular acceleration? Before we do that, there is one more thing that I want to do. I want to convert force also into its rotational analogous. What is that? That is torque, moment of force. So for that I need to multiply with r on both sides, where we know that A is equal to alpha r. Now is our opportunity to change A to alpha r. If we do that, we see that r into F is mr square alpha. This is torque. This is torque. This decides how much will be the angular acceleration of the body. And what is mr square here? Mr square here in this equation is the proportionality constant. Okay. So this is our torque, this is angular acceleration, and mr square is the proportionality constant, also called moment of inertia. Just like we have F equal to ma, this is going to be the new standard equation for rotation. In F is equal to ma, force is the cause, acceleration is the effect, m is the constant of proportionality which depends upon your body. Similarly, in this equation, torque is the cause and alpha is the effect, angular acceleration is the effect, where mr square, moment of inertia, is your constant of proportionality. Okay. Now for some time we are going to be focusing on moment of inertia. We will see what are the different ways and situations in which moment of inertia is going to come up. We will practice some questions on that as well, and then we will come back to this equation. For a system that is made up of multiple blocks m1, m2 and m3, they are all, let's say, located at distance r1, r2, r3, rotating about a common axis. What would be the moment of inertia of this system? In this situation, we need to add moment of inertia of each and every particle about the axis. So it will be m1 r1 square plus m2 r2 square up to whatever number of particles you have. So for a system made up of multiple particles, moment of inertia will be given by this summation. Okay. Now let's look at some questions based on this. Here in this diagram, an equilateral triangle is given and there is a particle of mass m, m and each and every vertex. So here is an axis which is like this, and the whole system is rotating about that axis. We have to find moment of inertia of all three particles, basically the entire system, about this particular axis. So as far as this object is concerned, it does not have any distance from the axis, moment of inertia will be 0. What about this and this? These two are going to be at equal distance from both sides. Here I am assuming that this axis is the perpendicular bisector. This will be given to you in the question. Okay. In that case, the distances are going to be a by 2, and final answer for total moment of inertia will be ma square by 2. What if the situation is like this? Here the axis is not passing through the center, in fact it is passing this way, but it is parallel to the previous axis that we have discussed. Later on we will discuss parallel axis theorem as well to solve the same question, but right now let's just see how to get this answer by summation. So in this situation, distance of this particle is 0, distance of this particle is going to be a by 2, distance of this particle is going to be full distance a. So what would be the answer? 5 by 4 ma square. 0, a by 2, a are the distances of these particles. Now what if our system does not comprise of individual particles, instead it's a continuous body? If it's a continuous body, let's say a rod of certain length L, this rod has length L and mass m, and we want to find moment of inertia of this rod, then what do we need to do? We need to divide this rod into tiny particles, okay, and find their moment of inertia and add them up. This process can only be done through integration because the particles are going to be infinitesimally small and infinitesimally close to each other. So how do we find out how much is the mass of this small particle over here? So we take an elementary portion at distance x of small distance dx. dx is the incremental length in x, that is the small change in x, and in that zone how much mass is present is dm. Now this mass dm multiplied by the square of this distance will be the moment of inertia of this small particle. But to add up all such particles, we need to integrate. So moment of inertia of dm is dm into x square. Integrating this, we will get our answer. But we can't integrate x with dm. X is another type of variable, m is a different type of variable. We need to have this equation in terms of a single variable. So we need to find a relation between x and m. How is mass related to this distance? Here the assumption is going to be that this rod has uniform mass density, linear mass density. The way mass is spread out along the length of this rod is uniform. Okay? Then we are going to use a concept that you have already done in your earlier grades, unitary method. So how will that happen? Imagine that you have 15 oranges and the cost of them is 30 rupees. If you have one orange, the cost is going to be 30 by 15, and for 3 you just multiply the 3 with your per unit price. Let's do the exact same thing to find out mass of that small section. So here we will say L length has mass m. So unit length, one unit length will have mass m by L. So then dx length will have mass m by L into dx. This is our dm. This is dm in terms of x. This is what we need to solve that integration. So here if I substitute that value now, dm is m by L dx. And in integration, whenever you have these constants, they come out of integration. So m by L is going to come out here. And now inside, I need to integrate x square with dx. During this integration, you can see that our rod starts from here. So if the rod is starting from here, the value of x is going to be minus L by 2. My rod ends here, so the value of x here is going to be plus L by 2. That is the reason why limits of integration are from minus L by 2 to plus L by 2. Now what is integration x square dx? X cube by 3, and then we substitute the limit to solve for the answer. So x cube by 3, then we substitute the upper limit, we substitute the lower limit with a negative sign in the middle, we simplify the expression and we solve for the answer, which is ml square by 12. Okay, this is moment of inertia of this rod about an axis which is passing through the middle. What if the axis was not passing through the middle, instead it was passing from this end? Everything will stay the same except the limits. You will again take length dx, small increment dx, small mass dm, and you will write the exact same expression. It's just that your rod now will start from here x equal to 0 and it will finish at x equal to L. If you do that, you should get an answer ml square by 3. Please try this yourself. Now let's move on. So this was one example of continuous body, right? But there are many such continuous bodies. We're not going to derive moment of inertia of each and everything, right? Your school's not going to even ask that. So now let's look at some standard objects. There are some standard objects for which we need to remember what are the moment of inertias. So for a rod, if the axis is passing through the middle, we know it is ml square by 12. From the end point, it's going to be ml square by 3. For a ring, it's going to be mr square, given that the axis is also the axis of this circle. For a disc, it's going to be mr square by 2. For a hollow cylinder, it's going to be mr square. For a solid cylinder, mr square by 2. For a hollow sphere through the diameter, 2 by 3 mr square. Solid sphere through the diameter, 2 by 5 mr square. And lastly, a rectangular plate. In this rectangular plate, if there is an axis which is vertically like this, moment of inertia will be ma square by 12, where a is this side. If the axis is this way, then it's mb square by 12, where b is this side. And if your axis is passing through the intersection of diagonals and your rectangle is rotating about that, it's going to be ma square plus b square by 12. You can generate this result by perpendicular axis theorem as well, which is coming up next. First axis theorem that we have to learn is a parallel axis theorem. What is parallel axis theorem? Or more importantly, when can we apply parallel axis theorem? Okay, this parallel axis theorem can be applied across any type of object, 1D, 2D, 3D. You don't have to worry about that. But there is one condition though. The condition is one of the axes must pass through center of mass. That's why this is ICOM. And the other axis needs to be parallel to this first axis. That's why the name is parallel axis theorem. So what is this theorem? It says I equals ICOM plus md square, where m is the mass of the full object, d is the distance between two parallel axes. What is ICOM? Moment of inertia about this first axis which is passing through center of mass. These are the only two conditions that you need to take care of, and then you can apply parallel axis theorem. Let's look at an example. So here we have a rod. An axis passing through the middle of the rod has ml square by 12 as its moment of inertia. For an axis which is parallel to this but passing through the end will be ICOM plus md square, which is basically ml square by 12 plus m into L by 2 whole square, which is ml square by 4. Taking an LCM, which is 12, you will eventually get the answer ml square by 3. This is exactly what I told you in the list of standard bodies as well. Now I'm going to show you the derivation of parallel axis theorem. If your school has not done it, you can completely skip this part, or if you are curious to know, carry on. So here, this is a randomly shaped object. There is one axis which is passing through the center of mass, and I have labeled it as ICOM. And there is another axis which is parallel to this axis, and this is passing through point x0, y0 in xy plane where z coordinate is 0. Whereas this is passing through origin. Center of mass is labeled as origin here, and I am intentionally, for simplification purpose, taking these axes parallel to z axis. While applying this theorem, you just need to take care that these two axes are parallel to each other. That's it. But for simplification of proof, we are taking this parallel to z axis. Why does that matter? So if this is your z axis and this is a point, changing z coordinate will move the point parallel to z axis, which means the distance from the axis is not changing. So the distance from the axis is independent of z coordinate, right? So you have less variables to work with. So your distance is only going to depend upon x and y coordinates. Okay. So here, what will be the distance of x0, y0? That distance will be root of x naught square plus y naught square, which is our distance d. D is the distance between these two axes. Okay. Now, if I take a point over here and its mass is mi and coordinates are xi, yi, what is the distance of this point from the origin? Distance will be root of xi square plus yi square. So what will be moment of inertia? Moment of inertia will be mi into square of this distance, which will be just xi square plus yi square. And if I add all such particles, if I do a summation over here, I will get ICOM. That's all I need to find total moment of inertia about this axis. But if I have to find my moment of inertia about this axis, then distance must be measured from this axis. And the coordinates of this axis are x naught comma y naught. So we are going to use distance formula for all the same particles. How will that work out? So it's going to be summation of mi times xi minus x naught square plus yi minus y naught square. This is your distance formula. And since we are using square of the distance, there is no root on this term. Let's open these brackets. If we open these brackets, what are the terms that we are getting? Xi square, x naught square, and minus of 2 x naught xi. Then yi square, y naught square, and minus of 2 y naught yi. Right? If I club these green terms together, I will end up writing this term. So that will be mi xi square plus yi square. Why is it important to club them together? Because you see this was our ICOM. If I club x naught square and y naught square together, I will get this term. What is this term? X naught square plus y naught square. That is the d square. So this is basically md square. And what am I getting through these two terms? Here I have taken 2x naught out of the summation. Why? Because it is constant. What is the variable? Variable is mi xi and here mi yi. This variable summation mi xi is gonna be 0. Why? Because this is from the formula of calculating x center of mass. And where is x center of mass? It's on the origin itself. If x center of mass is on the origin, this summation will be 0. Similarly, this summation will also be 0. If these two terms are 0, then I is equal to ICOM plus MD square. Isn't it the case? And that is exactly what we wanted to prove. This is the proof of parallel axis theorem. Now let us discuss perpendicular axis theorem. What is perpendicular axis theorem? Perpendicular axis theorem is to be used more carefully. Why? Because this is only valid for 1D or 2D objects. Here z-axis is normal to the plane of the object. If you have a 2D object, let's say you have a 2D object like this, then your z-axis has to be normal to the plane of that. Okay, this is very important. So first you make sure never to use this theorem for a 3D object, only for 2D object, and then the axis needs to be along your z-axis normal to the plane of the object. And then x and y are gonna be into the plane or along the plane of the object. So the theorem simply says Iz equal to Ix plus Iy, and you have to make sure that the three axes are perpendicular to each other and they definitely intersect at a point. Okay, all these conditions are required for us to apply perpendicular axis theorem. Now let's look at the proof of perpendicular axis theorem. Proof is very simple here. As I said, perpendicular axis theorem can only be used for a 2D object. So here, if this is my 2D object, I'm assuming this is the z-axis, this is my x-axis, and this is my y-axis, and this 2D object is in xy plane only. So this is the axis which is normal to the plane of the body. Okay, so if this is my x-axis, and if I take any random point over here with its coordinates xi and yi, what is the distance from x-axis? That distance will be yi. Y coordinate gives us the distance from x-axis. Similarly, this point, how far it is from the y-axis? It is xi distance far from the y-axis. So if I have to write moment of inertia about x, ix, that would be summation of mi yi square, because the distance from the x-axis is y. Similarly, if I have to write iy, it's going to be summation of mi xi square. What about iz? If I have to take z-axis as my axis of rotation, then this point is going to rotate like this. So then this is the distance we need, which is root of xi square plus yi square. So while writing the expression for moment of inertia, it will be summation mi xi square plus yi square. And this expression, if we separate, is nothing but iy plus ix. Hence, iz is equal to ix plus iy. This is the proof of perpendicular axis theorem. Now let's look at an example where we can apply perpendicular axis theorem. This is an example. In this question, we have a ring, and we know that moment of inertia about this axis is mr square for a ring. We want to find out how much is the moment of inertia about a diameter. So here I am taking two diameters. This is along x and this is along y. First thing to keep in mind, can I even do this? Is this even legit? Yes, it's a 2D object. We can definitely apply perpendicular axis theorem. Okay, then iz must be normal to the plane. Okay, that condition is also true. And now I have created ix and iy in a way that they are in the plane of the body, and all three of them are mutually perpendicular and they intersect at a point. All conditions are valid. Now we can proceed forward, right? So here there is one key feature which is specific to this problem. That feature is that your moment of inertia about this and this is going to be identical. Why? Because these are two diameters. Diameters are identical. There is symmetry here. So basically, ix and iy must be equal to each other. And if they are equal to each other, while applying this perpendicular axis formula, we can simply substitute iy as ix only. If we do that, we are getting mr square as 2 times ix. So how much is ix? Mr square by 2, right? But iy is also mr square by 2 because they are identical. But it doesn't have to be only x and y. This can be said about any diameter. Only in this diagram, I am taking the two diameters this way. I could have taken one diameter like this and another diameter perpendicular to it. As long as it intersects here, this will work, right? And since all diameters are identical, this moment of inertia of mr square by 2 is going to be the same about any diameter. I hope this example was clear. Let's move forward. Radius of gyration. What is radius of gyration? Imagine that we have an object and there is certain moment of inertia of this object mr square by 4. If we were to remove all the mass of this object and place it at a single point, how far shall we place this object such that moment of inertia does not change? So in that case, it's mk square, because all the mass is here at a distance of k, equals mr square by 4. If that was the case, how much is k? R by 2. So k here will be called radius of gyration. I have written the definition as well, right? But it's the exact same thing that I explained to you. Let's look at two examples of moment of inertia. So here there is a question in which we have to find moment of inertia of a disk about its diameter. We will do the same thing that we did for the ring, right? So we can take one diameter like this, another diameter like this, name them ix and iy. And iz is already known to us because of list of standard bodies that we discussed. So this is mr square by 2. If that is the case, then iz is ix plus iy. All the conditions are being met. It's a 2D object. The three axes are perpendicular to each other. They are intersecting at a single point. Then I can say Ix and Iy are equal to each other, so this is simply 2 times Iy. So how much is Iy? Iy is mr square by 4. And the same thing is applies here. In this case as well, we can apply this theorem across any diameter, which means all diameters will have moment of inertia mr square by 4. Okay? What if the question is this? In this case, we have a disk and moment of inertia about a tangent is being asked. Here if I take a line parallel passing through the center, then this will become ICOM, right? And we just solved the answer for this exact question because this happens to be the diameter as well. So how much is this ICOM? mr square by 4. But in this case, these two are parallel, so we can use parallel axis theorem. Parallel axis theorem says I is equal to ICOM plus MD square, where D is equal to R. So mr square by 4 plus mr square, 5 by 4 mr square is the answer. Okay, this was all about moment of inertia. Now let's move forward to torque. What is torque? Torque is rotational analog of force. Torque can be found out by doing a cross product of R and F. What is R? Position vector of point of application of force from the point about which you are finding your torque. What is F? Force vector. But if you just need modulus, if you just need magnitude of torque, this can be written as Rf sine theta or R perpendicular into F and R into F perpendicular. What is R perpendicular? Perpendicular distance of line of action of force. What is F perpendicular? Component of force perpendicular to position vector of point of application of force. I will show you an example how to apply this and this, but before that let us review cross product. Let's see how to apply this. I'm not assuming anything about you. You might not remember this. This was done in topic vectors. It's been a long time. Let's look at one example. So the question is, find torque of the force F vector 2i plus 3j plus 4k applied at a point A, which is given as 4i plus 4j, about a point B, which is 4i. So here I have intentionally chosen an example in which torque is not asked about origin. It is asked about a specific point. So your R vector is not this. R vector has to be found out by difference of this and this. Let me show you a diagram to explain what is this. What is happening over here. So A vector is this. So force is being applied over here. So force is being applied like this over here. This is the point of application of force. And B vector is this. We need to find the torque about this point. We are supposed to find torque about this point. So then the position vector R is this, which is basically A minus B. A minus B is going to be the position vector R. So 4i plus 4j minus 4i gives you 4j. So while finding torque, when we do R cross F, we have to use our matrix method ijk 0 4 0. Why 0 4 0? Because this is just 4j cap. So I is 0, k is 0. And force vector 2 3 4. How are we going to proceed forward from here? So we will write I cap. When we write I cap, remove this column, remove this row, multiply 4 with 4 minus 3 with 0. This is our expression. Then minus j cap, block your j column, 4 times 0 minus 2 times 0. This is your j. Then plus k, block your k, 3 into 0 minus 2 into 4. This will give you an answer 16i minus 8k cap. Okay, I hope this is clear. Now let's look at another situation in which we are not going to use cross product, in which we will learn how to use these two, and there will be conditions in which one will be a faster method over the other. Let's look at the question. In this question, it says find torque about the hinge. This is the hinge. This object is like a plank or a rod which is hinged at this particular end, and force F is being applied here at an angle theta along the length. So here R vector, position vector R is this. So we want to find torque about the hinge. We just need to find the magnitude of torque. If we need to find the direction, we can also write clockwise or anti-clockwise in certain situations. So here, from like just looking at the diagram, you can tell that force is going to be providing anti-clockwise torque because it's acting this way and this is your hinge. Okay, let's use our first method, R perpendicular into F. If we have to use R perpendicular, this is our R vector, but we need perpendicular distance from line of action of force. This is force, so this is the line of action of force. And now we need to drop a perpendicular on this line of action of force. If we do that, this angle is theta, this angle is theta. This is R, so this is a right angle triangle with this being 90 degree. This hypotenuse is R. So adjacent component is going to be R cos theta, the opposite one is going to be R sin theta. So when we say torque is R perpendicular into F, it's going to be simply R sin theta times F anti-clockwise in direction. Okay. How do we use R into F perpendicular? To do that, we need to resolve force vector. So when force is this way, it has a component which is F cos theta adjacent and the opposite component is F sin theta. So F perpendicular will simply be F sin theta, torque is RF sin theta, once again anti-clockwise about this hinge. Of course, this is much faster, right? But that won't always be the case if you are writing any competitive exam. Now let us look at a very simple example for balancing the torque. Here you can see that there is a rod which is balanced across this pivot. So on the left side at 1 meter from the pivot there is 10 Newton force being applied. On the right side at a 3 meter distance force F2 is being applied. What should be the value of F2 such that your rod does not rotate and stays in equilibrium? So we need to find how much is the torque of this F1, right? If this is your axis of rotation, you can see that this is providing anti-clockwise torque, and similarly F2 is going to provide you with clockwise torque. Okay, if we balance these two torques, we will get the answer. How much is the torque of F1? 10 Newton into 1 meter, that is 10 Newton meter anti-clockwise. How much is the torque of F2? F2 is unknown, multiplied by 3, that is clockwise. If we equate the two, 10 Newton meter anti-clockwise equals F2 into 3 meter clockwise, cancelling, you will get the answer 10 by 3 Newton. Now let's look at this next question. So over here we have a rod and this rod is hinged at the left end and its center of mass is not in the middle. This rod has a center of mass on the right side over here at a distance L by 3 from point B. Question is, find torque of gravity about hinge, center of mass and point B. So over here, to solve this question about hinge, how much is the distance of this mg from the hinge? That's going to be 2L by 3, therefore the answer mg into 2L by 3. Okay. How much is the torque of gravity about center of mass? Gravity is acting at center of mass. So will there be any torque? No. Answer will be 0. No torque about center of mass. Okay. About point B, how much is the distance of mg from point B? That is L by 3. Answer will be mg L by 3. Okay. Now let's look at application of torque equals I alpha. I started this lecture by explaining what is alpha. Then I went on about I. Now we are discussing torque. First we discussed torque at equilibrium. Now we will discuss torque when there is no equilibrium, when there is alpha. Okay. This equation torque is equal to I alpha can't be randomly applied about any axis. This has to be either about center of mass or about axis of rotation. This next question will clarify this. Let's see. So here we have a rod of length L and mass m. Center of mass is in the middle. Okay, so mg is acting right from the center. We want to find out how much is alpha about that axis of rotation. So we are going to use the equation torque equals I alpha is only valid about axis of rotation or about an axis passing through center of mass. So we can apply about this axis of rotation. If this is my axis of rotation, how much is the torque of mg? The torque of mg is mgl by 2. Is there any other force that is applying torque? There will be some force from the hinge, but there is no torque from that hinge. Why? Because the perpendicular distance is 0. Only mg has a distance from here. So therefore, mgl by 2 is going to be I alpha, where I is ml square by 3. If you are putting your torque about that end point, your axis of rotation is that. So therefore, moment of inertia should be about the same axis, ml square by 3, giving you an alpha of 3g by 2l. Okay. Now let's look at another question that builds up upon this. In this question, it's the exact same rod and they are asking us to find acceleration of center of mass, acceleration of a point on the hinge, acceleration of a point on the right end of the rod, and value of hinge reaction. Okay, we have already found out what is alpha for this situation. We know alpha. Now based on this, we have to answer all of these questions. If alpha is known and they are asking for this acceleration, what type of acceleration are they talking about? They are talking about tangential acceleration, with which I started my lecture. Okay, so tangential acceleration AT is related to alpha with this equation, A is equal to R alpha. That's all we need for our first part. So when we say acceleration of center of mass, it's going to be alpha into L by 2, because center of mass is rotating in a radius of L by 2. Alpha is 3g by 2l into L by 2 is going to give you 3g by 4. Acceleration of point on the hinge. Point of the hinge cannot move. Answer is 0. Of course, you can do this by 0 being the radius, but that's not going to move. C part. Acceleration of the point on the right end. For the right end, you will take the full length of the rod. So that's going to be alpha into L, 3g by 2. Now D part, find value of hinge reaction. Alpha A was easy. How are we going to find hinge reaction? First of all, why should there be a hinge reaction? Imagine your rod without hinge reaction. If there is no hinge reaction, if there is no hinge itself, the rod is simply going to fall down like this. It's not going to rotate, right? So what is the hinge doing? The hinge is applying some force at the end point so that the rod can rotate and not just simply fall. So how are we going to find this force? Newton is the only guy who can save us. So here again we are going to use net force equals mass times acceleration from your topic Newton's laws of motion, right? Net force is equal to mass times acceleration. But which mass and which acceleration? Here it is going to be total mass of the body and acceleration of center of mass. We have seen that acceleration depends upon the radius. The further you are from the center, greater is your acceleration. But we need a single acceleration for Newton's law equation, and that's going to be center of mass. Okay, so the equation will be mg minus r, downward force minus upward force, is the net force. That will be m times a center of mass, which is 3g by 4. We found that here. Once you solve this, you know r is going to be mg by 4. mg by 4 is the hinge reaction. Next concept, kinetic energy of rotation. When it comes to kinetic energy of rotation of an object, the kinetic energy depends upon two things. How is the center of mass moving and how is the object rotating? If both of these things happen together, we need to find their kinetic energy of both of these things and add them up. Imagine a situation in which an object is rotating as well as moving forward, right? So kinetic energy of translation is going to be half m VCOM square, where VCOM is the speed of center of mass. This is your kinetic energy, which is due to the motion of center of mass. And then Kinetic energy of rotation is going to be half I omega square, where I is taken about center of mass. So this is I center of mass. And the total kinetic energy will be simply the sum of these two, which will be half I omega square plus half mv square, right? But all of this can be reduced to a single formula, which is going to be much faster if you know what is axis of rotation. Okay, in that case you can simply say that kinetic energy total is half I about axis of rotation omega square. Let me show you an example. Let's imagine that we have a rod which is hinged at this point, the same rod that we were discussing before. It's hinged at this point, and then it is moving with omega about this hinge. If it is moving with omega, then we know that VCOM, V is equal to omega R. That's going to be omega L by 2. This is your VCOM. So what will be kinetic energy of translation? Half m VCOM square, which is half m omega L by 2 square, which is 1 by 8 m omega square L square. Okay. What about kinetic energy of rotation? Kinetic energy of rotation, half I omega square, where ICOM is ml square by 12, and this is 1 by 24 m omega square L square. If we add both of them, we will get 1 by 8 plus 1 by 24. The variables are same, m omega square L square. LCM is going to be 24, numerator will be 3 plus 1. Final answer 1 by 6 m omega square L square. But we would have gotten this by this in one step. How? This is simply half I about axis of rotation omega square. It's the same answer, right? So why do you need to know this? Because in the exam they can ask you separately to find kinetic energy of translation or rotation. If it is total, then use this formula directly. Okay? If nothing is mentioned, then what to do? Total is the default. Whenever kinetic energy is being asked, total is always going to be the default. Now let's do a question based on this. Here in this question, we have a rod which is initially horizontal, and when we let go, it swings to a vertical position. If the rod is released from horizontal position at rest, find angular speed and speed of center of mass when the rod becomes vertical. Initially it is horizontal, we let go, it starts to move. At this moment, what are the speeds? What is angular speed? What is speed of center of mass? How can we solve this question? We can solve this question by mechanical energy conservation, right? Why is the speed coming in at first place? The speed is coming in because the center of mass is moving down. Center of mass moving down means is gravitational potential energy is decreasing. If gravitational potential energy is decreasing, kinetic energy is increasing, right? So if we have to conserve mechanical energy, that's going to be sum of kinetic and potential initial and sum of kinetic and potential final, right? What is initial kinetic energy? 0, because we are starting from rest. Initial potential energy also 0. I'm assuming this to be the reference. You can assume your reference anywhere in the question. For the sake of convenience, I'm assuming it here. So my initial potential energy is 0. Final kinetic energy, since I need only total, it is convenient to write half I about axis of rotation omega square. And final potential energy minus mgh, because it is moving down by distance h, which is L by 2. Now I'll take this negative term to the other side, and then I will substitute I as ml square by 3. Solving this, we will get the answer omega equals root 3g by L. Here, how do we find VCOM? As this object is rotating, what will be the speed of center of mass? That's going to be omega into R. You see, this is why the first part of the lecture was the most important thing. So V is equal to omega L by 2, giving you root 3g L by 2. Now the next thing that we are going to discuss is angular momentum. When it comes to angular momentum, we are going to discuss two scenarios. First scenario is when there is a point mass moving in space. If there is a point mass moving in space, Let's say this is our mass m, it has velocity v vector, and the position of this is given by r vector, and we want to find angular momentum about origin. Okay, so in that case, angular momentum is given by r cross p or r cross mv, right? This will give you, the cross product will give you the exact vector value along with the direction. But a lot of times we are only concerned with the magnitude. When it comes to the magnitude, we can simplify this formula just like we did for torque. Okay, so that's going to be L magnitude is equal to R perpendicular into P. What is R perpendicular? Perpendicular distance of line of movement. If this is my line of movement, then what is the perpendicular distance from here? This will be the perpendicular distance from here. Okay, or we can do the other thing as well. The other thing was R into P perpendicular. So in this case, component of momentum perpendicular to the position vector of the mass. So in that case, if this is the direction of momentum, it has one component this way and one component this way. We simply take this one, multiply with R and get the answer. Okay, so this situation has this as the angular momentum formula, which can be either used this way or this way as well if only magnitude is required. But what if you don't have a point mass but you have a rigid body? A rigid body is made up of many such point masses. In that case, we will need to add angular momentum of all of those point masses. But fear not, we don't have to do integration. There is a simpler formula. That's what we're going to do. And that formula is I omega. So we simply say, what is your moment of inertia about axis of rotation? Multiply this with omega, and that will give you angular momentum of this rigid body. Example. So in this case, imagine that we have our rod, our favorite, mass m, length L. So in this case, angular momentum will be ml square by 3 times omega. This is the angular momentum of this rod. But why did we even discuss this? Why angular momentum? You see, when it comes to straight line motion, why did we introduce momentum, or when was momentum introduced to you? While explaining Newton's second law. What was Newton's second law? That force is directly proportional to rate of change of linear momentum. Right? The word linear was not there because that was the only type of momentum that you were introduced to. So force is directly proportional to rate of change of momentum. In rotation, the same thing changes to torque being rate of change of angular momentum. So just like we had F equal to delta P by delta T or dP by dt, torque is equal to dL by dt. So here, if total external force on the system is 0, linear momentum is conserved. Just like that, if net external torque on a system is 0, angular momentum is also conserved. Most of the questions on angular momentum in your exam are going to be about conservation of angular momentum, and they will mostly be about rigid body rotation. Okay? They can add some particles as well, but basically what you have to do is you take your I, right? Even if there is a rigid body along with some particles, just count the particles while calculating I. Imagine that you have a disk, and on that disk there is another particle. So moment of inertia of the disk mr square by 2 plus moment of inertia of that particle, which is mr square, that will give you total I, and use this angular momentum formula to conserve the angular momentum. Okay? Now let us look at an example question for this. So the question says, if Earth shrinks in a way that duration of a day becomes 18 hours, what would be the new radius in terms of old radius? Okay? So in this case, we are assuming Earth is shrinking, because of which the duration of the day is changing. How is that happening? Because if the radius reduces, moment of inertia reduces. If moment of inertia reduces, omega increases. What is the underlying assumption here? The underlying assumption is that there is no alien intervention here. There is nobody applying external torque. If there is no external torque, we can conserve angular momentum. Okay? So here time is related to omega. How? T is equal to 2 pi by omega. So initial omega is 2 pi by 24 hours. Final omega 2 pi by 18 hours. And if we use our conservation of angular momentum equation, I initial omega initial equals I final omega final. And then we put the values. Earth being a solid sphere is going to be 2 by 5 mr square rotating about its diameter. Omega initial 2 pi by 24, then finally 2 by 5 m small r square, assuming that the radius has changed, into 2 pi by 18, right? You can see 2 pi, 2 pi, 2 by 5 m, everything is same, that's going to cancel. The only thing that is different is r square by 24 and r square by 18. That's going to come up in the next step, and if we cancel and solve, we will get r as root 3 by 2 capital R. This is the answer if there is a question about conservation of angular momentum like this. Okay, the last concept over here is about calculating work and power. How do we calculate work in this case? Just like we found out the formula for angular momentum, similarly we will do this. So when it comes to work and power, work for a straight line motion is given by integration f dot dr, which will become dot product of f and delta r for a constant force. For rotation, it will be integration of tau dot d theta, which will become tau dot delta theta if it's a constant torque. Power for a straight line motion is a dot product between force and velocity, which will now be dot product between torque and angular velocity. Okay, this was all the theory of rotation. Please practice some problems before going for the exam. If you need any help, let us know in the comments. If you have any suggestions about the next videos, let us know that as well. And then we will make summary videos, whatever shortcut tricks you want for whatever chapter you need. That's it from my side. Thank you very much. Videos everyone, let's start. Oh sorry, this is YouTube.